Once you take the self-coupling to infinity and you decouple the Higgs, what you get is a Lagrangian that will have, whose kinetic term will have nonlinear interactions between these Goldstone fields that live on the SU2 sphere. Okay, and then you can actually try to compute this explicitly just by writing this down as an SU2 matrix, and here you can come up with this vector will become can be parameterized just by two angles, three angles. Right, because this would be a very general SU2 matrix that you can get just by expanding this matrix from the exponential. That would be like something like sine of theta e to the I alpha, and something that has determinant 1, and that's self-adjoint. That's U bar U equals 1. And okay, and then you have this type of structure, and then once you substitute this into the kinetic Lagrangian, then you get lots of interactions that go as like theta squared plus and then you have like this becoming as an axial angle, and then the alpha plus sine square theta square, right? And it has so the Lagrangian has this type of structure of a nonlinear single model of this sphere, and then this Lagrangian, well, without in the absence, this comes multiplied by rho square, and then once this radial field is frozen, then this violates unitarity. So it violates unitarity, and it has this type of nonlinear interactions that depends on the derivative of the fields. So it's a good candidate for classicalization. And actually you can do better. You can add, let me call this L. You can have a Lagrangian that goes as L, which is just the nice kinetic term that violates unitarity for these Goldstone fields, plus L squared, because as it turns out, this cannot, once you couple it to some external fields, this cannot do the job alone for classicalizing. So once you have this L square here, then you get the type of interactions that you, exactly very, very similar to the interaction that you get in the Goldstone case. So you can expect it to classicalize the standard model. Or the other option would be, if you couple the Higgs, you leave the radial mode on the theory, and then you couple it to some T mu nu, or, well, I mean, I need to do it in a gauge parameter.
Now you're going beyond the question.
Beyond the question.
You're not asking.
Just unitarity. Yeah, this would be.
You were just asking about unitarity.
Okay. It was nice listening to you. So.
Okay.
So how would you experimentally see, or could you discriminate between classicalization and...
Oh, the problem is that, as far as I understand, in the latest review that we had on the subject, that would be slightly hard, because the type of things that you can look at are this is the type of suppression that you get, the type of exponential suppression of high modes. But you in the standard model, as far as I understand, you could actually have the decay 2 to 2 or 2 to 3 or something like that, but you wouldn't have like these many jets. But
so you're asking within, you mean within the, you're asking
in the LHC or
within reachable experiments? Or?
Yeah.
Yeah, because within reachable experiments, as far as I understood from the reviews and from talks with Vali, in the low energy you would have a hard time identifying the difference between the classicalization and just natural Higgs resonance. But if you go to, for instance, very, very high energies, then it would be a very obvious signal, because you would produce a very a big classicalon that, and this will decay into very, very soft, lots of quanta.
That's not true. Suppose your colleagues from LHC at some times, like in 4 years from now, they will come to you and tell you, we have seen a particle with 126 GeV, say, and all couplings are as we thought they would be to other particles.
Okay.
Then you would say this is not indicative for having measured Higgs particle.
Oh, okay. Yes,
Yeah, you mean if they find Higgs, of course they find
yeah,
Higgs.
that's exactly the case. Because
if you see the Higgs, you see the
yeah,
Higgs,
but
right?
what I'm thinking is that you could like hand draw a model of a classicalizing theory that would give you this exact sign that would look like a Higgs, I imagine, just by...
Well, not the light one, no.
Yeah,
no,
yeah, just
not the light one.
126
Not 126 would be... Well, unless you see resonances.
Yeah.
Yes.
If you just see 126 Higgs...
That's true. If it's not just the Higgs, but if it could be Higgs plus other things, then it might be difficult to discriminate, right?
If it's 126 Higgs and let's say you go to 400 and you have nothing, then for sure it's not classicalization, has nothing to do with classicalization. If you see 126 Higgs type thing, then next one somewhere above, like I don't know, at 200, and then you see another one at somewhere, then it's a different story. But of course they haven't seen anything at 200, so probably. So if you see 126, then it's Higgs, yeah. I mean, or something else.
Yeah, well, 126 plus the right couplings, because still in the couplings could be hidden other.
No, of course, no. But I'm saying, what I'm saying is that if you see something which is, let's say, 250 or even if it looks like carbon copy of the normal Higgs,